again, good morning, good afternoon, good evening, wherever you're joining us today. I hope you're safe and well. This is Keith Strier from NVIDIA. I am the Vice President of Worldwide AI Initiatives, and we have a purpose at NVIDIA, which is to level the playing field and to democratize access to the infrastructure that makes AI at scale possible. And the truth is, before I joined NVIDIA, which was about 14 months ago, I didn't spend a lot of time thinking about the infrastructure, thinking about the technology underneath the AI. I focused, more on the strategy, on the policy, on the use cases, on the risks, on the applications, on the implications of those applications, but much less frequently on the infrastructure. And that's okay. But the artificial intelligence just doesn't happen. There's a very specialized computing stack that includes the hardware, the software, and the networking and all this technology. And without that computing stack, AI doesn't happen. And AI isn't one thing. AI is a constellation of different technologies and methods. So a single stack or a single stack has to be configured in many different ways to accommodate the different kinds of AI workloads and applications. And that stack can also be distributed in many different areas. And understanding that is actually quite important depending on where you are in the ecosystem. And the notion that you can just flip it on and off like a light switch, like a traditional classical computing stack, is actually a myth. It's not that simple, certainly not at scale. And that's why companies like NVIDIA, like Huawei, like the other companies in the industry are playing such an important role in the enablement of AI. So but I'm going to really look. I've got about 20 minutes, and I'm going to walk you through this journey in essentially 3 stages. We've got the what. I'm going to explain to you what, and I'm going to start with a little bit of history on NVIDIA, because one of the questions that almost always comes up in every meeting, certainly before the pandemic, when we're sitting in rooms, is, well, why am I talking to NVIDIA at all? I mean, what does NVIDIA have to do with this conversation about artificial intelligence and AI compute and supercomputers? And I thought NVIDIA was just a gaming company. And that's a great question. And I'm going to explain how one connects to the other. It's really actually quite fascinating. So there's the what, and then there's the how. Okay, so I get what we're trying to do. So, but how is that actually happening? How is that coming into being? And then the last piece would be the why. Why is this important at all? So let's get into that. Look, 70% of the world's gamers get lost in synthetic worlds like Fortnite and Minecraft, powered by NVIDIA, and we love that. And we're completely dedicated. That's our heritage as a company, and we're dedicated to sticking with that. We'll continue to invest in exciting new architectures and technologies that make these worlds come to life. The company was founded 27 years ago on the premise of just making graphics exciting. And by reinventing graphics, they launched the modern era of gaming. It started on the PC, and then it moved to consoles, and then of course people game now on mobile devices as well. And very soon you'll be walking around with your virtual reality or augmented reality headsets. You'll be gaming in that way. And so the gaming keeps evolving. It's the number one sport in the world, right? Esports, very competitive. So we love that. But there's more to it, right? I mean, the reason why the gaming has become so interesting and the graphics, so compelling, is because it's really about performance. It's about the ability for the computers to process, the specialized mathematics behind the imagery and the visualization of these incredible synthetic worlds. And Jensen and his co-founders, they invented this processor, called the GPU. And now the first one was actually in the 90s, but I think the first one or two didn't do as well commercially. This was the really successful one here in 2000, the GeForce 256. And this really launched the modern era of gaming, which incredibly led to the modern era of AI. And what's so fascinating about this story is that over the sort of 20 years, from 2000 to 2020, the same computing stack, right? The same architecture, the same chip technology, the same software, all this entire stack that powered gaming evolved and got stronger and faster and more versatile to also power the workloads in the world's largest data centers, the world's most prestigious research institutes, in enterprise supercomputing systems, and ultimately in smart devices all across the edge. And we'll cover that too. So here we are in 2020, and NVIDIA is not just a gaming company. It's not just a gaming company. It's also not just a semiconductor company. And that's important because that kind of, again, we're just going to explain the story of what we're talking about. It's more than just technology powering graphics. At this point, that computing stack is now powering 333 of the world's top supercomputers. Top 500 is the standardized list, of sort of a commonly used benchmark. And across the board, you'll see NVIDIA technology accelerating 2/3 of all of these supercomputers. So that, why does that matter? Again, let's get to the how. I mean, how does this? I'm sorry, the what. What is the impact on the world? So supercomputers are fascinating. And again, before I joined NVIDIA, I'm pretty sure I had never seen a supercomputer or touched a supercomputer. So I wouldn't even know what that was before the summer of 1999. And then I remember going into the data center at NVIDIA and standing in front of one of the most powerful machines ever designed by man. These machines these supercomputers turn researchers into superheroes, right? I mean, everything you can possibly imagine, from modeling the known universe to modeling Earth itself in a high fidelity way, predicting climate change, forecasting weather, developing being able to mimic human behavior as well as at the molecular level, being able to create new materials which lead to new kinds of machines like aircraft. I mean, there's just they're the kind of huge, big science questions and big science opportunities. It's really not possible without these machines. So if you actually look, and I haven't done this, but if you actually look at sort of the progress of science and the scale of discoveries we're making in so many fields, it maps pretty closely to the progression of supercomputing, because you can ask questions, but if you need 300 years to answer them, it's not going to make a big impact in your lifetime. But if you can consolidate that discovery process and that search, right, and you can accomplish that in what used to take centuries to years to months to minutes to seconds, then that does change the fundamental progress of science, and you see that playing out. So now let's do a very quick flyby, okay, of what that looks like. And this is, for the most of you who don't know anything about this topic, this is going to blow your mind. If you're actually an expert in supercomputing, or you know a thing about this, I'm gonna kind of put your hands over your ears, ignore this, because I'm gonna just sort of do a very high level explanation of some of the performance benchmarks. We're not going to go into peak performance and LINPACK benchmarks and the floating point integers. We're just not going to go there. It's completely pointless. This is about we'll call CEO level math, but this is really interesting. So in 2007, IBM built this system called Roadrunner. There's a picture of it, and these are large machines that filled large data centers, and this was the first time in history. Now, most of you were doing something else. I don't know, where were you in 2007? I'm sure you did not catch this headline, because you would have had to really been looking for it and be a kind of a super nerd. But the first time a supercomputer passed the 1 petaflop mark was in 2007. There you have it. What is 1 petaflop? Well, that's 1 quadrillion or 1,000 trillion. Okay, that means you'd have to just give you a reference point. If you could do 1 calculation per second for 31 million years, that's 1 petaflop. That's what a 1 petaflop computer can do in 1 second. So again, we're talking about calculus at a level that is mind-blowing. So this machine was built. Again, it took several years to build this machine. Started planning in 2002 and live in 2007. Cost 120 million to build, and 300 cabinets of servers, thousands of servers. So, but this was an important milestone in the history of supercomputing and ultimately science. Now, 5 years later, you've got the Titan. Now, the Titan cost about the same, a little bit less, but it was a full 1/3 smaller, so 100 cabinets less. So it needed far less compute to and roughly the same cost, but it was 17 times more powerful. So 5 years, 17 times more powerful, 1/3 the size, but still a very big machine, right? I mean, this is one view, but if you had a top-down view, you'd see 200 cabinets is still a lot of cabinets and thousands of servers. So, okay, but that's it, right? You went from Roadrunner to Titan. Now let's jump ahead 6 more years, 2018. Now this is a monster. This is Summit. This is the first supercomputer that was designed from scratch to be an AI supercomputer. What does that mean? Well, supercomputing, runs this specialized mathematics to support big scientific, simulations and scientific equations. But artificial intelligence is a very specific kind of mathematics, a very specific kind of modeling. And up until this point, the supercomputers didn't really operate exclusively or in general around AI. But now, starting around this time, these computers were actually engineered and optimized specifically to support artificial intelligence. And this machine, let's just do the mathematics for a moment. In 2007, just 10 years earlier, it was 100 million to achieve 1 petaflop. Now you jump ahead to 2018, it's 200 million, twice the cost, but it's 200 times faster. So in 2007, 1 petaflop cost $100 million to achieve. And in 2018, 1 petaflop cost $1 million, right? So the cost and the technology came down a factor of 100 times, right? So very, very powerful. And of course, it was 10 times faster than the previous generation. So you could really see this huge, huge impact. But now let's jump ahead just 2 years. This is Selene. Selene is the computer that sits as one of the 4 or 5 supercomputers that sits in NVIDIA's headquarters. This is our supercomputer. This is the 7th fastest in the world. It's the fastest industrial-owned supercomputer in the United States, and it is 1,000 petaflops. That's 1,000 times 1,000 times a trillion. Okay, way too many zeros to even worry about. And we call that an exaflop. But here's what you need to know. Not only is this 5 times faster than the world's fastest computer 2 years ago, but it costs less than the IBM Roadrunner computer that was built in 2007. In fact, I don't know the exact number, but I think it's probably potentially half as less, somewhere in that ballpark, a half to a third less expensive than the fastest computer that was only a single petaflop in 2007. This is 1,000 petaflops and costs far less. But more importantly, or maybe just as importantly, when they built Roadrunner, that took 5 years to plan and build. This computer was set up in weeks, 3 weeks out of the box. So the ability to take these machines, to scale them quickly, to operate them, and to operate them efficiently and sustainably has changed dramatically. So that's the what. Now, everything doesn't happen in a data center, right? Those are the biggest machines in the world, and there's hundreds of them, but they're not all in a data center. Some sit in the public cloud, right? Like an Amazon or an AWS. Some of them sit at the edge now. We could squeeze that technology down. Obviously not as powerful, but nonetheless performing artificial intelligence inside devices like factory robots and cars and even on satellites in space. So the other concept here is that AI doesn't just happen in big machines and data centers. It really happens across the entire spectrum now, from the cloud to the edge. And it's important to understand that because that helps you. Ultimately, you need to distribute that technology as close as possible to where it needs to be executed. That changes the economics, the security. It's really quite dynamic. So, and as you can imagine, this age of AI, we have this just 1 trillion connected devices. It's endless. So we need to figure out how to put that technology where it's going to be most effective and consume the least amount of energy and that kind of thing. Now, that could also be a simple robot delivering you pizza, right? It doesn't have to be, it doesn't have to be a building or a data center. And what I want to just quickly show you, if you look at the little images there, the Jetson, right? Those are the brains, right? And so you would take that brain, whatever is the right size, and you'd put it inside your little Postmates, autonomous on-demand urban delivery robot. Now that brain is what's operating that robot in action, but you're still going to use a supercomputer, whether it's in the cloud or in your data center, or whatever it is. That's where you actually create you train the robot to be a robot, essentially. It learns, and you train that model in a much larger machine, and then you take that algorithm and that knowledge, in a sense, and you squeeze it down into this what we call an inference model, and we put it on a much smaller supercomputer in the machine itself. That's sort of the basic architecture of this entire new generation of smart technology. And of course, if you're talking about a car like the Mercedes, and by 2024, all the Mercedes coming off the assembly line will be powered by NVIDIA, and they're basically going to have supercomputers in the trunk, right? I mean, backed up by supercomputers at HQ and supercomputers in the cloud. So You just got to think of this incredibly diverse distributed network of AI supercomputers from the cloud to the edge, making all these things possible. And it's hard to imagine that that's what's going on behind the scenes. But if you don't understand that computing stack and the hardware and the software and all the geniuses that are working on those systems, of course, the humans, then that none of these things actually come into being. All right, that's that execution you were talking about. Now, that's the what. Now, how about the how? I mean, how is this happening? I mean, what's really happening behind the what to bring to life? And this is one of the things that's happening. A couple of weeks ago, the Wall Street Journal declared that Moore's law is no longer dictating the trajectory and the progress of compute as it relates to artificial intelligence. The silicon chips, that entire stack that powers AI, now more than doubles. Doesn't just double, it potentially more than doubles every 2 years. And it's attributed to both hardware and software. And that's very different than Moore's law, which really was focused on pushing the boundaries of design in just the physical chips themselves. When you combine the hardware and the software, you can achieve something that's much more exponential, right? Since 2002, in the last 7 or 8 years, NVIDIA has improved the performance of its system, not just its chips, but its system 317 times. Now, why do we need to do that? Well, in addition to wanting to relentlessly pursue higher performance, we have to do that because the models themselves, the actual data science demands it. The OpenAI Forum did a study, and I think it was last year, so these numbers have probably even gotten more intense. But when they did the study, they found that the actual size and scale of these AI models that data scientists are working on double every 3.4 months. So imagine, by the end of a single year, they would have gone up, an order of magnitude of 12 times, just within 1 year. So if you're in a procurement process and it's taking you 2 years to design, procure, and stand up a new supercomputer, and that was based on requirements from 2 years ago, then by the time that system goes live, it's already too small. It doesn't have enough power to keep up the scale of models that have been anticipated. This is one of the challenges. It's one of the reasons why you need to not only make better chips, but you got to innovate across that whole stack. And that's something that that we have been working on for years. And that is part of the reason why Wang's law has replaced Moore's law, because it's not just about pushing the boundaries of design and manufacturing. That's important, and the whole industry keeps doing that. But you have to innovate on the software. You have to partner with the most common open source frameworks and accelerate them. And you have to build ecosystems of partners who then accelerate on top of your stack, right? And so you've got layer after layer after layer after layer of amplified, multiplied value. That's how you get to this sort of full stack innovation exponential curve, and which is why the systems are improving in the tens to hundreds to thousands of times of performance over the course of a short period of time. Now, that's the how, that's the what. Let's get to the why. Why does this matter at all? Besides that, it's really interesting to talk about if you're kind of a geeky, nerdy person. Because AI compute is the foundation for a new economic model. That's why. AI is the new critical infrastructure. It's always been this engine for scientific discovery. As I said earlier, supercomputers turn researchers into superheroes. It attracts great scientists. It brings prestige and funding, fosters international collaboration. But that's all still true. It's very hard I think it's probably impossible to win a Nobel Prize now if you were not attached in some way to a significant supercomputer to support the work that you're doing. But it's no longer just about science. These same machines that have been driving science for years and decades, these are now the engines for economic growth. They are powering industrial innovation, service innovation, customer experience innovation. They are fueling startups, creating jobs, helping people achieve their dreams. So supercomputing and the convergence with AI is no longer just about science. It's about prosperity, right? It's also about a platform for public innovation. These machines and the science around them are helping make governments more accessible. It's about helping detect and deal with infectious diseases, which is obviously very, very important in the current environment. It's about planning and designing and building and operating brand new cities and different kinds of urban experiences. None of that is possible without the scale of computing and that infrastructure. You can talk about it. We can have conferences like this all week long, but if you don't have that infrastructure, then it doesn't actually happen. So what's happening in parallel to that, the other why to this question is really what's happening on a policy basis. And at the same time that computers and data science and data scientists and academia, and there's all this innovation exploding in the startup ecosystem, in parallel with that, you have this global policy imperative. You have these national AI programs, which, may, if you've been coming to a couple of these conferences, it probably sounds like, oh, this has been going on for a while, but it hasn't. This is a relatively new chapter in human history. Before 2017, there wasn't a country on earth that had a national AI policy. So, and then the first one was Canada, but now they all kind of have this, follow a similar path. There's different, there's a recipe for these. They almost all are sponsored at the highest levels of government, prime ministers and presidents, that kind of thing. They have a strategy that then gives way to policies and laws and regulations. They talk a lot about the ecosystem, which is everything from academia to industry, and then ultimately they have a focus on infrastructure. And you really need to have these. And then the good plans, quite frankly, anchor themselves to very specific outcomes and goals that are accountable to the citizens. Economic growth is usually number one, but things like public health and safe cities and national security, these are all very important. And every plan, and there's probably 60 or 70 now countries in the world that have them, have a slightly different focus or theme, like responsible AI is one that's more popular recently. But these plans, this sort of top down, because it's really been a very top down exercise. When you combine that with the explosion of innovation on the infrastructure side, has created this this new era of modern AI, and it's really unique. Now, one of the ways to look at that is to ask yourselves, okay, so if we understand how NVIDIA is this gaming company is now right up there, helping to drive this modern era of AI. And there are other companies that are important in this mix as well. Like I said, Huawei and Intel and AMD and lots of other companies are part of this ecosystem. The cloud companies, Amazon, Microsoft, Google, and you name it. This is a very robust and broad ecosystem of partners. But one of the ways to look at the impact is look at this top 500 list, which is an industry standard way of measuring the scale of these computers. And what's really interesting, if you look through it, what you'll find is that only 28 countries in the world are on this list. And the vast majority of computers, if you look at the top of that graph, sit in two countries, China and the US. So if you actually take out China and the US, then you do have 26 other countries that are sharing, the remainder of the computers. But there's a lot of countries that do not have a computer on the list. And that usually didn't matter. That never made the nightly news. That wasn't on the front page of the Wall Street Journal, because you really didn't care about that unless you were maybe, in a very, unless you were in a science role, quite frankly. So yes, it was a source of prestige. It still is a source of prestige, but it wasn't tied to bigger, broader social goals. And that's a mistake, because going forward, this technology is not just going to be driving the national agenda around science. It's going to be driving the national agenda around prosperity and growth and global competitiveness. And that's why this list is going to change. And, one of the reasons it's going to change is because we are democratizing access to that infrastructure. What used to require hundreds and hundreds of servers, 600, 700 servers, 20, 30 racks, right? You saw those pictures of those big machines that filled up an entire room. We've now taken that and we have put it into a single rack. Now that matters. That isn't just about a faster, less expensive computer. That is a game changer. That creates a new kind of haves and have-nots. Small countries that could not participate in AI, who need to participate in AI because it is one of the levers for growth in a global digital economy, can now participate. Having a massive AI supercomputer used to take years and cost tens or hundreds of millions of dollars. That is no longer true. You can have a very credible supercomputer in the single digit millions of dollars, and you can have it in weeks to months. That is what AI infrastructure looks democratized. And here's my last slide.
Okay. I've got some questions as well.
Yeah, so this is the last slide. And this is what, this is our purpose, enabling all nations to become AI nations. And these are just announcements we've made in the last 30 days, from India to Czech Republic, to Italy, to the UAE, Vietnam, to Slovenia, the largest supercomputers in the world, to, all across the world in every hemisphere, trying to really enable everyone to participate in this global economy. So that's my presentation. I will stop now and we can do some questions.
Okay, excellent. Thank you so much. Thank you so much, Keith. That was really, really thorough. Very A lot of topics in there. Particularly fascinating was the notion of enabling new economies. And you put it really well, a crisply quotable remark, how supercomputers can support researchers, and researchers can secure more funding, and we can celebrate greater innovation, and society ultimately benefits. I hadn't actually considered it in such terms as that. I've got 3 quick questions,
Sure.
and I'll say short because we've got a couple of minutes. So sure. As we know, NVIDIA is dominating in the GPU market. Why is that? Is it because of great hardware, software, or both? What would you say is the magic, the secret weapon, secret sauce?
Well, it doesn't hurt that we invented the GPU. So that's probably, you'd have to go back to that. In the mid 90s is when Jensen and his co-founders conceived of it. So that gives us a little bit of a leg up. Look, it's a competitive market. I mean, there's no question about it. Very competitive market. We don't take that. We take that very, very seriously. And we have great respect for our competitors and all the companies in the space, and we think it's a good thing that there's, but I do believe it is a combination of the hardware and the software and the ecosystem. You can't win on hardware alone. You really need that full stack, and I think that's something we didn't just figure that out this year. That's been the model for a decade. So I think that's our main advantage.
I think that absolute execution example you raised of the supercomputer built in 3 weeks, which is, I can remember a time trying to play with a motherboard. It would take almost 3 weeks. So absolute kudos. Another question, are GPUs sufficient for all kinds of AI algorithms? And how do you see the future? Will there be a need for custom ASIC chips anymore?
Again, I think, look, we're in the early stages of artificial intelligence, which is hard to believe because it's been around for 50 years. But we're, in terms of the industrialization of AI and really understanding its applications. And I think the specialized hardware stack will continue to evolve as well. And I think, look, I believe, and I think we believe GPUs will continue to play a very important role in that stack, including when quantum computing comes around, which will need large scale GPU accelerated systems to crunch the mathematics that come off these, those systems. So I don't think it's a competitive situation. I think it's a matter of just, there will be different segments to the computing stack, and they will all respond and to certain kinds of needs and workloads. So I think we'll continue to stretch the versatility of the stack that we have, but there'll be additional stacks, and I think they'll operate in parallel and in tandem.
And final question then. Well, actually, I have a quick one myself. Are you able to say which type of countries or any more countries in your pipeline for having a national AI policy? Are they all predictably Western Hemisphere, or any notables in the pipeline?
I want to be careful not to call out any specific country too much, but here's what I'll say. Look, there's, Mark was saying this towards the end of his presentation, that it's important to execute, and the truth is we have gone through in a very short period of time, just a couple of years, you have 60, 70 countries, and you have some of the smallest countries like Lithuania and Vietnam that have published national AI strategies, which is terrific. Because you got to have that, but I think now we're in this phase where, well, people need to stop talking about AI policy and they start to investing in AI programs, and you're definitely seeing a separation from the wheat and the chaff there. And quite frankly, some of the larger countries are struggling with the politics and the complexity of their legacy sort of infrastructure and societies and their political machines, where some of the smaller countries are moving faster. And so that's not, now I would say they're moving faster, but they have to. There's more of an urgency for them to stay as relevant in that new sort of economy, the fourth industrial revolution. But it is actually impressive. We are working with the biggest countries, but frankly, from an AI nations perspective, our partnerships tend to be with smaller countries that want to move more actively and aggressively. So I think that's actually going to be very, very interesting. You're going to see countries that are relatively small punching above their weight in AI. And I think that's something that you would not have seen in prior generations.
Okay, and then final question, and thank you for your patience to the panelists waiting. We heard about the deal between NVIDIA and Mercedes, and you cited it in your presentation as well. Have you any more comment on how it may well NVIDIA will play a role in the automotive industry?
Yeah.
And do you see it comparing to Tesla et al.?
Yeah, so look, we have a very simple philosophy. If it moves, it's going to be autonomous. So it's not just about cars, it's about boats and trains and airplanes and everything. So we are, look, we are building we have taken our stack from gaming and our capabilities in simulation and our stack in AI, and we've now sort of evolved it into a full end-to-end stack for robotics, both training, simulation, and enablement. And we expect to sort of help advance that software-defined infrastructure conversation across the entire spectrum of robotics and powered machines like cars. So I would say in the next 2 years, you're going to see a flurry of announcements and other similar kinds of deals across other industries, and specifically cars, which is, I mean, transportation, the entire spectrum from mobility, on up, is going to be it's a very exciting area. And I think the autonomous nature of these machines, the need to make them intelligent. And I'll just say there was just a headline the other day where the U.S. Air Force updated the software of one of its planes in flight for the first time. So it actually uploaded a patch in its operating system, which is just unheard of, and so again, whether it's got wheels or wings or rotors, I mean, I think you're going to see an entire new generation of technology, and we think NVIDIA is going to play a big part in that.
Okay, Keith Strier, Vice President of AI Initiatives at NVIDIA. Fantastic talk, very, very inspiring. I hope the speakers didn't mind it starting into their time. It was a useful precursor. Thank you once again, and feel free to follow up with Keith online and socials.